What's up, folks? So in this video I'm going to tell you more about how to get started with GraphML. So I'm wrapping up my exploration of graph machine learning, and I wrote this blog on how to get started. So I thought of just creating a video and maybe telling you more about my opinions on some of the stuff that I've already written in the blog, and giving you some complementary ideas. So yeah, basically stay tuned and hopefully you'll learn something new. Okay, so the first thing I want to talk about is this. So research can be really tough, and just be aware that every single top-notch researcher you know of, or engineer, or successful business person, whatever, has hard days, and it's not always easy. So I'm talking from my own experience. So it's not always mentally easy to stick with the plan and execute and do the research, read the papers, code up that project. So just be aware of it, that you're not alone in this, and you should never give up. That's my only advice I have to give you. Never freaking give up, okay? Secondly, don't get demotivated by the people who appear to be super successful in something. So the thing is, most of them are really specialized. So I like to think about this from this linear algebra perspective. So it may be nerdy, but there is a method to this madness. Basically, I want to say the following. So among all of those different dimensions, all of the things you could be doing, researching, learning about, let's take two axes. So one axis would be maybe somebody who is just reading research papers. So some fictive person that's only reading research. On the other hand, you have people who are just coding something, who are working on some deep learning libraries, like maybe in the context of GraphML, that would be PyTorch geometric. And most people tend to be somewhere in between. But there are a lot of people who only read research paper and they never implement something from scratch, or never work on anything that has to do with engineering or coding. And I want to tell you that they don't know many details, even though they appear to understand everything because they curate their own content. They don't know many details of how stuff works. And I'm talking from my personal experience. So until I start coding something up from scratch, I don't understand thoroughly how much I actually don't know, if that makes sense. So you want to be somewhere in between. If you want to be a really successful researcher, in my opinion, and you want to boost that H-index, if that's something of interest to you, you should probably be focusing on reading research papers a lot, but you should also make these, let's call them detours, into implementing something and actually playing with the code. On the other hand, if you want to be a great engineer, and you probably want to focus on code, but you still want to research and allocate some time to read research papers, because otherwise you'll just lose the pace, and the field is progressing very rapidly, and you gotta allocate some time to do the due diligence. Having said that, let me walk you through this blog. So first, GraphML, and hopefully you know what GraphML is. You heard about graphs, so those are those data structures, and GraphML is just a bunch of machine learning models, so that learn on top of that graph data. And the first thing I want to advise you here is, especially if you're a perfectionist, you'll tend to be like this. I want to go on a tangent here and maybe invest 3 months of my time and get some solid background in graph theory, a branch of mathematics, or maybe get a really good foundations in the network analysis field. And I want to tell you, you don't need to do that. You can jump straight into the field and make a first step, and without doing all of those detours. So it's totally fine to start reading this blog and start with high-level resources, and that would be your as a first step on your journey through graph machine learning. Sometimes you may want to take a step back, or maybe better said, make a side step, and invest maybe 3 months of your time into building up more solid mathematical foundations. And me personally, last year in 2020, I invested maybe around 3-4 months into reading this book, Mathematics for Machine Learning. And it's a bit complex if you're intermediate or even beginner, but it meant a lot for me, and it helped me better understand the stuff that I later learned. So the strategy of doing side steps and investing into some foundations is also a good idea sometimes. So that's GraphML. You have machine learning, you have machine learning models that learn on graph data. instead of images or text, like in computer vision or NLP, you're learning from graphs. And now, before we start, before I show you the resources, let me just walk you through some cool applications. And one more thing to note, you'll hear a lot about graph neural networks here, and for the sake of, for now, just think of them as neural networks that work with graphs and somehow can process those graphs and do the classification or regression on nodes or edges or even the complete graphs. So just have them as a black box on top of your mind, okay? So first things first, GraphML is such an exciting topic because the applications you'll see here are so much different from those you'll see in the computer vision or the NLP worlds. So there in computer vision, you'll be seeing algorithms that manipulate images or videos, and in NLP you'll be seeing algorithms that manipulate text. And those are all pretty homogeneous. So even though you can do, I don't know, facial landmark detection, pose estimation, bunch of things, segmentation, regressing 3D models, bunch of things in computer vision, they're all still kind of related. And then when you start doing GraphML, you understand like all the plethora, like the vast like diversity of different applications you can do with graphs. So two cool applications I want to start with are recommendation systems. And if you're not aware already, like in my opinion, recommendation systems are the single most important and influential piece of AI currently in 2021. So you interact with recommendation systems all the time. YouTube recommendation, Facebook, Twitter, Pinterest, whatever, just name it. And you have recommendation systems influencing your decisions. So before I started making YouTube videos, I wasn't fully aware of it, and now I'm getting a thorough understanding of how influential recommender systems are. So basically, as an example, I've seen many videos which are really top-notch, high quality, that have 5K views, and not because the presenter was anything less eloquent or the content was worse. No, it was just because he or she came on later, and so he or she is not on the front page, like among the first queries. And then you'll see some videos which were made maybe 2015, 16, 17, and they have amassed a lot of views, and so that's what YouTube will recommend you. So what I've learned is I now tend to go past the first 5 results. Before I would just open the most viewed videos, but now I'm completely aware how recommendation systems can actually bring you inferior recommendations, unfortunately. And engineers and researchers are working on this, and one way is to just kind of use graph neural networks. So because the problem, as you can see here with Uber Eats, for example, you can really nicely model all of these problems as graphs. So here you have a graph between users and food, and Uber Eats has a separate graph between users and restaurants. They still haven't merged the two together, even though I think they're currently working on it, or maybe they recently even deployed it. I'm not aware of it, but yeah, this is the last news I'm aware of. And so just processing this graph data, you can make better recommendations to your users. And obviously I won't get into all of the details. I did some videos on PinSage, that's the recommendation engine at Pinterest, and you can check out that one somewhere here in the card. Okay, so you can kind of see how the graph neural network PinSage improve upon these baselines. Here you can see people carrying some logs, and here you can see the visual. If you just take the visual baseline, it will bring you images that are like really similar when it comes to appearance, because they're also grayscale, but you can see the semantics, like here the soldiers, and here you can see actually the trees and the logging. So PinSage got both the semantics as well as the appearance successfully by leveraging both the graph structure as well as the visual textual information that's available in those graphs on those platforms. So those are some nice applications. And aside from recommendation systems, we have these basically fake news detection GNNs, and that's so important. The societal benefits of deploying really successful fake news detection algorithms are so important. And again, you can see here, maybe on Twitter, you have a single tweet, and somebody retweets a tweet. That would be a second node, and you have the edge, and so you can build up the graph. And basically, these networks can figure out the propagation patterns of those retweets. And just by looking at the propagation patterns, it was shown in previous research that we can figure out whether the news is actually fake or real. And again, that's a really naturally modeled as a graph. So GNNs to the rescue. Aside from this app, there is one more cool app, which is basically figuring out the probability that you will produce certain event depending on your neighborhood and whether they did the same thing. So, for example, to be less abstract, maybe the goal is to figure out whether you'll retweet a tweet if some of your neighbors retweeted the same tweet. That would be one concrete example. And again, you have the graph structure that you can leverage to regress these probabilities. So various cool applications. And what's even more interesting is that GraphML, so all of these are still kind of familiar to you, but like GraphML goes into these deep fundamental science problems and can naturally solve them. So one of them would be this example I gave with the neutrino detection, where basically the setup is the following. You have a huge cube of ice, and you have these light sensors interdispersed in the distributed throughout this ice. And what happens is a neutrino comes out from the space and hits the ice and interacts with the ice molecules, and in that interaction something that's called Cherenkov light emits, and basically those sensors, those light sensors, can catch that light, and you can basically see certain nodes of that grid-like structure of sensors get activated, and then you can just deploy the graph neural network on top to figure out whether the neutrino came from some certain events we care about, like supernova explosions or whatever. So I don't know about you, but like this completely blew out my mind, because usually you see neural networks applied to images, videos, text, and that's it. And here you can see fundamental science and GNNs being used to solve them, to solve those problems. Okay, yeah, there are many other apps. I'll skip some of them, like figuring out the molecules that can help beat cancer, because you can see you can model the thing naturally as a graph. Again, you have genes, you have proteins, all of those interactions, and you have some molecules or drugs, and you model it as a graph, and you can find interesting information like which molecules can help treat cancer better or prevent cancer. Then you have drug side effects. When you combine multiple drugs, you want to be sure it would be beneficial if we could computationally calculate the possible side effects, because the combinatorics is so huge here, and it's impractical to do it in a lab setting. In vivo, we need to do it in silico or computationally. So many cool applications. So the last one I'll note here is the one that was gained a lot of traction last year in 2020. Basically, we as a society have a huge problem with antibiotic resistant bacteria. So the reason that happens is because people are misusing antibiotics. They're using them for viruses, they're using them to treat common colds, and you shouldn't be using antibiotics in those cases. You should be using a specific antibiotic, if you're sure you have a certain bacteria that this antibiotic can inhibit. And because of all of those misuse, there is a threat of this bacteria which is resistant to every single antibiotic, and that's like the worst nightmare in the science community and in the medicine in general, pharmacy. And so what this graph neural network did is it was trained on a set of these specific molecules, and then and was trained to figure out which of these molecules tend to inhibit one specific bacteria, namely the Escherichia coli in this example. And then once they deployed the trained graph neural network onto a specific new data set, it was able to filter out 100 candidates that gave a high response, a high probability that this molecule will inhibit Escherichia coli. And then they just delegated that small subset of molecules to scientists, and they were able to find this molecule called Halicin, which basically can treat, which was basically found out to be a super potent antibiotic and extremely successful in inhibiting Escherichia coli. And previously, it was just they considered this same molecule for its anti-diabetic properties. So those are just some of the super exciting applications of graph neural networks, and I hope you found this interesting and that it motivated you to further investigate the graph ML field. Now let me just kind of make a brief detour and compare graph ML with computer vision and natural language processing. And I personally think it's really important to try and connect the ideas from various subfields of deep learning, because by doing that, by just creating those connections, I think you'll be better to generate much better research ideas, and it's just cool to kind of make this connection. Just gives you some kind of satisfaction as well. So basically, you can treat computer vision or images and videos in general as just a special case of graph, which is highly regular, and we call these grids. So you can see here a 4x4 pixel image can be represented as this specific graph, and here we have 4 neighbors. In general, you can have up to 8 neighbors because, you have the diagonal pixels as well, and you have the top left, top right, bottom left, bottom right. And that means we can actually deploy graph neural networks to solve computer vision problems. And same goes for NLP, because sentence is just basically, you can treat sentence either as a fully connected graph or maybe just as a tree. And but the thing I want to mention here, and I mentioned that in the blog as well, is don't fall into the trap into thinking that you can better solve these problems with graph ML. So the thing is, certain biases that CNNs have, like having weight sharing and localization, are super useful, and we show that that's much more efficient than using graph ML. In some cases, though, you can use graph neural networks and perform better. So when I say that, I mean the following. Transformers are a special case of graph neural networks in a sense. So once you have a fully connected graph, transformer is basically a graph neural network that operates on a fully connected graph. And it was shown in 2020 in October, I think, the vision transformer, that we can use transformers on images to improve upon CNNs if we have enough data. So if you have a huge amount of data, it is possible maybe to use transformers or graph neural networks to achieve even better results than by using CNNs. But there's a saying, if you only have hammer, everything looks like a nail. And it's really bad if you just have the graph ML context and if you don't know other fields, you're gonna try and use graph neural network for everything. Same goes for deep learning. And that's why it's useful to be aware of different fields, different methods, different techniques, because for every specific problem, there is a solution that's highly optimized to be used for that specific problem. Now, there is a trade-off between being as general as possible, like maybe GPT, and on the other hand, having a super specialized algorithms. So they are better, they are more specialized, they are more optimized, but then you have the overhead of some developers having to invest a lot of their time to now specialize to tune that algorithm for every single problem you encounter. On the other hand, you have these general architectures, you just apply them and they work on everything. You don't have to invest any more time, but they are suboptimal in every single of those problems. So that's the trade-off. Having said all of that, let me now walk you through the resources and the way, and just kind of advise you how you can structure your learning of graph machine learning, okay? So if I were you, I'd first start with graph embedding methods. So these are not graph neural networks, these are a specific class of methods which are similar to Word2Vec. If you're familiar with natural language processing and you know what Word2Vec is, these are going to be much more familiar and easy to grasp. So they're just repurposed Word2Vec onto graphs. So basically, for example, you have these algorithms, DeepWalk and Node2Vec and Planetoid, and what Deep2Walk does is the following: it just samples random walks from a graph, and you can treat those as a sentence. So if you treat the graph as a corpus of text and you treat that specific random walk as a sampled sentence, it's basically the same thing as Word2Vec. You just want to make sure that the neighboring words have similar embeddings. So if they tend to be close in those sentences, you want to make the embeddings really close. And if they never appear in the same sentence, if some words never appear in the same sentence, you want to make their embeddings really different. So that's the main idea of all of these methods. So take some time to kind of understand these, because all of these graph embedding methods can be used for exciting graph problems, like doing regression on top of those embeddings, or classification, both on node-wise level, edge-wise, and graph-wise level. So you should probably start with these, and that's gonna be it's gonna be a nice first step. Okay, in a way, it's orthogonal to the graph neural networks that I'm going to tell you about more in a second. So, graph neural networks. When it comes to graph neural networks, there are two main branches, and one is the spectral methods, and the second one is spatial or message passing methods. And my advice here is to take some time and investigate spectral methods, because the terminology and references will get propagated into the spatial methods, and you'll be seeing some terminology from the spectral methods. So it's good to kind of understand at least some basics about these. So having said that, if you're not familiar, if you don't have a strong base in like fundamentals in linear algebra, if you don't understand what eigenspace is, if you don't understand what eigenvector and eigenvalue is, if you don't have some understanding of the Fourier analysis or signal processing, this is going to be tough. Like you should probably just read some high-level blogs and try to kind of get familiar with the words and terminology, and don't kind of pull yourself down just because you don't understand everything, because as I told you, you'll need some time to understand it, especially if you don't have the fundamentals. But having said that, just go through it, get some feeling, because that's gonna be super useful for you, believe me. So the reason I tell you not to worry about them too much is because they are computationally very expensive, because how they work, you have something called GraphML, so that's just a huge matrix, and what you want to do is you want to calculate those eigenvectors, and that operation is very expensive. And not only that, it's that also these methods can generalize to different graph structures. So they have to be applied in a transducting manner, and can be applied to new graphs which are smaller, bigger, because they inherently are transductive. So that's the second pain point of these algorithms, but still, I told you, take some time and learn about them. Okay. In my opinion, again, and this video is full of opinions, you want to start with, as always, with a top to bottom approach. You want to start with some high-level videos, high-level blogs that will get you exposed to the terminology and new ideas, new concepts, without you having to understand every single detail. So you're just trying to build up that skeleton of knowledge, and you should probably start doing that by watching videos and reading through some Medium and towards data science blogs. So those are usually really nicely curated, high quality blogs and videos, and they'll get you exposed to the essential concepts. Having said that, you'll find some of the links here, and this video from the New York University. They're kind of publishing all of the lectures they hold there, so that's super useful for the community. And yeah, you should start with those. I mentioned the Fourier analysis and stuff. So if you don't know about, if you haven't watched this one, even if you know everything about Fourier, I strongly suggest you go ahead and watch Grant Sanderson's video on Fourier. So when I say Grant Sanderson, he's better known as the 3 Blue 1 Brown channel, and he's got a couple of videos on Fourier which are so nicely visualized. And if you don't have the background from Fourier analysis, this is probably going to be enough, like a high-level understanding of what Fourier is, basically decomposing your signal into a sum of differently scaled frequencies, and it's going to be a really good step for you to understand spectral methods if you don't have any background whatsoever. So do watch that one. I've linked 2 important papers here. This one is the most important one, Spectral Networks and Locally Connected Networks and Graphs, and ChapNets just kind of localized that method. When I say localized, I mean you just want to update a single node, you'll just use the k-hop neighborhood instead of using every single node in the graph, which can be huge. Like in some examples, when you're having maybe social network graphs, you want to make those algorithms localized. And secondly, aside from localization, ChapNets made it also more efficient to calculate these representations by just leveraging the Laplacian graph matrices and not calculating the eigenvectors I previously mentioned. Again, some higher level blogs, just go through those resources. You should probably literally sequentially be learning about these resources. I've linked, you should probably read the graph embedding methods after you do the high level blogs and videos, but whatever, feel free to experiment there, but you should roughly be following the flow of the blog. And as the blog progresses, we go into more research and more niche topics like dynamic graphs and like graph expressivity, etc. Okay, having said that, let me jump to spatial methods, and these are the methods you'll mostly be seeing. So those are networks such as GCN, graph convolutional network, networks such as GATT, graph attention network, then you have GraphSage, PinSage, many different spatial methods. And on the high level, they all work really similarly. So basically you do the following thing. So you have a node and you have the neighborhood. And what you do is you transform the neighborhood feature vectors somehow, maybe doing some linear projection or MLP, whatever. You somehow aggregate them, maybe doing a mean of those feature vectors or sum or max or whatever, and then you combine that central node's representation with that aggregated transform representation again somehow, and that's your new representation. And that's the general framework of message passing networks. And all of these can be considered as a special case of that framework I just explained you. I covered many of these spatial methods on my YouTube channel, so check them out: graph attention networks, graph convolutional networks, PinSage and GraphSage. So those are the 2 that were deployed in the recommendation system I previously mentioned in the beginning of the video. Message passing neural network is the one that introduced this general framework, general notion, and understanding that all of these methods are just special case of something and are doing something fairly similar to each other. 2 more papers you should probably check out is the gated graph neural network, which kinda popularized the usage of graph neural networks again, because they were initially, similar methods were proposed already in, I think, in 2004, 2009 period time frame, and this paper kind of popularized GNNs again, and it's a nice paper. It's really general, because it also includes the edge features. It uses the GRU, the LSTM for the aggregation I just mentioned, and so it's a nice read. Aside from that paper, Learning Convolutional Neural Networks for Graphs is a cool paper, because I didn't mention this, but like the spectral and spatial methods, what they try to do is generalize the concept of convolution that works so nicely in the computer vision world, so with CNNs, onto graphs. And that turned out to be quite a difficult, challenging problem in a way. And so there were different approaches. One was a spectral one was a spatial one, which is basically approximation of the spectral methods. So it's not as mathematically rigorous as the spectral methods, but they, as I already mentioned, in practice, they work really nice. And this paper here just introduced another idea, and that was to basically copy the concept from the CNNs more literally than mathematically, if that makes sense. So basically what they try to do is introduce the concept of node ordering into their method, because the main problem with graphs, and the reasons you just can't use a fixed kernel like you use in the CNN, is first of all you have the varying number of nodes. So sometimes a node will have only a single neighbor, sometimes it will have 1,000 neighbors, and you obviously can't use a 9x9 kernel or 3x3 kernel as it's commonly used in CNNs. So that's the first problem. The second problem, you don't have any concept, any notion of ordering. So like in CNNs you have top left pixel, you have top right pixel. In GNNs, you don't have that notion. So what they try to do is they try to linearize a neighborhood by doing something called graph labeling, and then apply the kernel that's always fixed onto those order linearized neighborhoods. And so it's a nice read. The idea itself didn't get that much traction, but it's an awesome read, and so do check it out. Okay, I'm wrapping up with message passing networks with this one, simplifying graph convolutional networks paper. What they figured out is there are some graph classes like homophilic graphs where you can use just much simpler baselines, the graph neural networks, and so this paper just showed that. So homophilic graphs are those graphs where the nodes that are connected have similar label. So that's a common thing you have in social network types of graphs, because usually people that have similar opinions tend to cluster together, and those types of graphs are called homophilic. And basically what this paper showed is that you can use a much simpler baseline. You can just leave out a multiple layered graph neural network and just use the aggregation on the k-hop neighborhood. So instead of using just a one-hop neighborhood, so your direct connections, you can use and do the MPNN, the message passing scheme I told you multiple times. You can instead do the following. You can just aggregate the neighbors from the k-hop neighborhood, where k can be maybe 3 or 4, which means you can get up to like 4 indirect connections, and build up, and then just use a single, so aggregate those and then use a single MPNN layer to build up a nice representations, which can even achieve better results than those complex spatial methods like graph attention network, etc. And they are much more computationally efficient because they are so much simpler. Now there is a nice parallel I can make, and I will make here, between the CNNs and this thing here. So if you know anything about CNNs, you know that back in 2012, when AlexNet was introduced and produced this thing called ImageNet Moment, AlexNet had 11 by 11 kernels. Whereas, so that's really broad compared to VGG, which in 2015 I think basically they figured out that using 3x3 kernels and much deeper architectures is actually beneficial. So you can see the parallel between this and CNNs, and basically with the arrival of certain ideas such as residual connections, such as batch normalization, we were able to make deeper and deeper CNNs and keep those kernels really small at 3x3 size, and that turned out to be really good. So much better than using large kernels and shallower networks. On the other hand, we can see here in GraphML that using big kernels and shallow networks actually produces better results on certain classes of graphs, not on everything. Sometimes you still need deep graph neural networks, and just keep that in mind. Okay, so those were the main methods, and now the topics that are following are a bit more esoteric, but nothing less useful from the previous methods I just explained, like embeddings and spectrum methods and spatial methods. So GNN expressivity is really interesting. So let me just explain what it is in a nutshell, and it's actually fairly easy when you put it this way. You see these two graphs here, and you can see that they are different. So how we also call that more like a more formal term for that would be they're non-isomorphic. And what you ideally want to have is you want to have your graph neural network assign a different embedding to two different graphs. That makes sense, to two non-isomorphic graphs. On the other hand, if the graphs are isomorphic, you want to assign them the same embedding, and that's the ideal case. So all of the methods I explained to you so far, like GCN, Graph Convolutional Network, or GET, are actually confused by this simple example. As you can see, the color histogram, we have 4 reds here, 4 reds here, 4 blues, 2 greens, and 2 greens. And the way how, for example, graph classification works, you just take all of these features, you kind of do a mean, and then you'll try to do some prediction. And because the histograms are the same in this particular case, that means we'll have the same embedding even though they are non-isomorphic. So that's the potential failure case, and we want to avoid this. And so by building more expressive models, they'll know how to cope with cases like this one. And that's the whole, so the field of expressivity deals with this exact problem, trying to assign the same label if the graphs are isomorphic, otherwise assign different not label, different embeddings, okay? So that's the whole concept, and this graph isomorphism network paper first showed that by using that GCN and GETs and all of those there are certain families of graphs which confuse those MPNN networks. And later a lot of cool papers appeared that do some subcount, that use substructures to increase the expressivity, or use multiple aggregation techniques like principal neighborhood aggregation paper, etc. But that's the basic idea I want you to take out of this. So yeah, just discriminating between the non-isomorphic graphs. Papers on exciting GNN applications, feel free to go through these resources. I already walked you through these, so yeah, just go at your own pace, and hopefully you'll find some interesting new papers, additional papers here. Okay, so handling dynamic graphs chapter. Okay, all of the methods I've explained so far are dealing with static graphs. So what's static, what's dynamic? So dynamic graphs are those that evolve with time. So either new edges or new nodes appear as the time progresses. Okay, so one good example would be social network. Maybe you have Facebook or Twitter, where each new tweet is a new node that appears at certain time point. The same goes with edges. Maybe somebody does a retweet, and that's a new edge that appeared dynamically in this graph. So the graph is constantly being pruned and increased. So it's usually always increasing, but there is some pruning happening when somebody deletes the account, deletes the tweet, whatever. For those types of graphs, we need different methods. And the two main ideas I want you to take out from this section is that you need to find a way to represent the time, which is a scalar, as a vector. And there are a couple of papers you can find. So I've linked some papers like TGN here, and you'll see some references inside, like Timetable, I think, which shows one of the ways you can kind of so map the scalar, the time, into its vectorized representation. So that's one crucial idea that's needed. And the second one is doing the concept of doing a temporal neighborhood. So basically you have a single node, let's say it's a tweet, and what you want to do is you want to aggregate only those edges that are maybe at most 1 hour like old, and you want to just ignore all of the other edges. Otherwise you have a huge graph, and you'd have this thing called over squashing problem, because you have so many nodes and you want to try to aggregate them, usually doing some mean or something, and that's a similar effect happens in those bag of words, if you're familiar with bag of words technique. So you kind of know that by doing bag of words, you lose the information. Same thing happens in RNNs, where you get this over squashing effect, because as the sequence becomes longer, you're kind of doing this bag of word thing, and you're losing the older information. So transformers, for example, tackled this problem by using the concept of attention, right? So you give more attention to more important feature vectors, and you ignore some less important ones. So yeah, basically temporal neighborhood helps us avoid that over squashing problem that happens in all of those bag of word methods, such as in RNNs. I linked a couple of unsupervised papers, unsupervised learning papers, like DGI and this variational graph autoencoder. So if you're not familiar with variational autoencoder, this paper probably won't make any sense. It's just, it has 3 or 4 pages. It's 3 or 4 pages long, and it already assumes you know everything about variational autoencoders. But it's a nice read if you're interested in learning more about these unsupervised learning methods. I made a small tangent here on this field called geometric deep learning. So when you start doing GraphML, you'll hear about geometric deep learning, that's for sure. And those are pretty much separate. It's a pretty much separate research area which deals with manifolds and not with graphs per se. So even though, again, you can treat certain manifolds, once you discretize them, they're basically graphs. But here, the same thing as with computer vision, the same thing as with NLP, you have a class of algorithms which are much better optimized to deal with manifolds, even though they can be treated when discretized as graphs. So just keep that in mind and don't make it too big of a detour into that field, because it's pretty much a separate research area compared to GraphML. Okay, with that out of the way, I linked a couple of cool visualization tools here, like iGraph. I've used iGraph personally in my Graph Attention Network project. Check that one out if you haven't. I'll link it down in the description as well. Aside from that, I've been mentioning datasets here, and datasets are so important, and they usually achieve they usually don't get so much attention in the community. Usually you hype something like, there's this huge model like GPT that has like 5 trillion parameters, and that gets really hyped up. But the datasets, which are so important for progressing the research, don't get so much attention. And there is a problem with GraphML that people used these Quora, CiteSeer, PPI, and PubMed datasets a lot over the previous years, and only recently have we started to integrate bigger real-world graphs and use them as benchmarks. So what happened is that when you use these let's call them toy benchmark graph datasets, like similar to MNIST in computer vision, you basically can discern between much more expressive and better models from simpler baselines. So that's the whole point of the benchmark, right? You wanna have a benchmark which clearly separates and sorts better algorithms from the worst ones. And here the margin became smaller and smaller, even between the simplest baselines and the most complex GNNs. So we needed new datasets, and so I linked this Open Graph benchmark, which is a nice initiative that introduced much better, much larger and more diverse graphs into this GraphML field, and that's a really good thing. And we should be very grateful for people who invest their time to develop better benchmarks, even though that's not as exciting as proposing some novel idea. Research is usually super incremental. Rarely do you see something that's completely new. Like graph embedding methods, Virtuec already existed. They just adapted it to graphs. Similarly, for most of these methods are just a variation on some research that already existed. Just keep that in mind. I linked some cool resources. Michael Bronstein's got a really awesome blog. Highly recommend you go and read those. But probably you'll want to leave those for a bit later, because he's a professor and he has his blogs are a bit more technical. So you want to start with those high-level blogs, read through resources I've listed, and only then start reading Michael's blog. Finally, once you get your foot inside GraphML, start following people on Twitter and start following Sergey's newsletter. I highly recommend it. That's a good way to keep in sync with the newest things happening in a specific field. So similarly to how Sergey has a newsletter in GraphML, Sebastian Huda has a really nice newsletter in the world of natural language processing. So yeah, this is something that was shown to be a nice format for transferring knowledge in the community, so you should be following these small specialized newsletters. Highly recommended. I'll skip through this. I made a couple of videos on Graph Attention Network project I did. So it gained a lot of traction, like it got 750 stars since I published it a couple of weeks ago, and you can go through it, you'll find it useful probably. I've got both the transductive as well as the inductive examples inside, like both the Cora, which is transductive, and PPI, protein-protein interaction dataset, which is inductive, and I've got the I made this Jupyter notebook as well, so yeah, do check it out. That's the project, and that's pretty much everything I wanted to tell you. Maybe a short note on some other detours you could be making, and that's, I already mentioned geometric deep learning, so it's in a way it's a separate research topic, so be aware, don't make a mistake and start reading those papers because they are pretty much independent, orthogonal to the GraphML papers. Then there is this equivariance deep learning subfield, which deals with making your algorithms much more statistically efficient by exploiting symmetries of your problem. So the same way as CNNs are translationally equivariant, they are trying to make models which are also rotationally equivariant, which can just exploit different symmetries. And again, it's a separate research subfield. Be aware of it. Don't waste too much time of going there if you just want to focus on GraphML. Even though, again, there is always some cross-examination of ideas, so you have to draw the line where you want to explore more versus exploit more. Finally, knowledge graphs. They're a mix between NLP and GraphML. So again, totally new terminology, totally new set of people, history, papers, so just be cognizant of that fact. That's it, you know the drill. Hit that subscribe button, hit that bell icon, and until next time, keep learning deep.